participates in. So if you have pyridine itself and you do an electrophilic aromatic substitution reaction, then you always get a slow process whereby you see substitution at C3. Okay, and the reason is the same one that we've seen every time before. You show the resonance structures for the charged intermediate, and it turns out that you end up with more stable resonance structures if you get C3 electrophilic aromatic substitution. Now, the reason this reaction is usually very slow is because under most of the conditions for electrophilic substitution, you actually have a large amount of the pyridinium ion and only a little bit of the pyridine. So the reactive species is there in a small amount at equilibrium, and that's why this is usually a slow reaction. The other reaction that we talked about was the electrophilic aromatic substitution of pyridine and oxides. And we said that when you do electrophilic aromatic substitution on the N oxide, this should remind you a little bit of the phenol. So when you see this, you should be thinking about a phenol. And in this case, you end up with the C4 substitution. And so since you can convert the pyridine N oxide back to the pyridine, this allows you a way to control the location of the substitution reaction. If you start with pyridine, it's at C3. If you first convert the pyridine to the N oxide, then it's C4. We didn't show the resonance structures for this particular process. That's something that you're asked to do in one of the problems in the chapter, so I urge you to take a look at that. So these are the two substitution positions that you have access to with an electrophilic substitution, okay? Now, pyridine, I said, had some kind of weird chemistry that was limited to pyridine, and certainly the reaction whereby you take a mid and treat it with pyridine and then end up with 2-aminopyridine, and what I'm going to show here is hydride. This is a very strange reaction, right? This is a known process. There's no counterpart that we've seen for this process in benzene. This is, of course, a type of a nucleophilic aromatic substitution. Hydride is a miserable leaving group, and I had a few things to say about the mechanism, but this is clearly something we've not seen before. We also said that you could take pyridine and treat it with, I think the example we gave was phenolithium, and get the same kind of substitution at C2 in modest yield, again with hydride as your leaving group. So these are nucleophilic aromatic substitution reactions. You can see that by choosing either a nucleophilic aromatic substitution or an electrophilic aromatic substitution, I can selectively functionalize any of the three positions of pyridine. Now, these reactions, of course, are not particularly good. So we said that now, there is a way to make this kind of process much, much, much better. And the way to do that is to use not pyridine itself, but say the 2-chloropyridine. So the 2-chloropyridine is activated towards nucleophilic substitution. You can do nucleophilic substitution at C2 of 2-chloropyridine using mild conditions, and you can do this in very good yield. And so that tells us that we actually can functionalize all three positions in pyridine one way or another. Now, the other thing I wanted to remind everybody about was the similarity between pyridine and carbonyl chemistry. And so this is something we talked about, I guess, last time as well. So if you look at this part of pyridine, if you look at this part of pyridine, just the red part, but that looks like an imine. Okay, so this should remind you of, it should remind you also of an aldehyde. Okay, so I have this, or if I have that, I always have a polarized carbon heteroatom bond, and so the same kind of reactivity that we've seen for ketones and aldehydes, we also see for pyridine. That was the introduction to that nucleophilic aromatic substitution chemistry. And so that's why if I change this to and make it into a chloride, then this kind of a 2-chloropyridine should remind you of an acid chloride. And so just as we have, just as this is a very good reactive species, reactive compound with nucleophiles, so also the 2-chloropyridine. And so the homology in structures is reflected in similarity in reactivity. And this is something that I wanted to point out. Now, there's yet another way to do nucleophilic aromatic substitution on pyridine that doesn't rely on having a chlorine here. And so if I can make a pyridinium ion, so just a methylpyridinium ion, for example, then this also should remind us of having this sort of ARB group here, having this kind of an oxonium ion, right? So if I have an oxonium ion, then where R is either a proton, or it's an alkyl, or it's a Lewis acid, or whatever, then this carbon atom is going to be much more reactive than in the aldehyde. So also the N-methylpyridinium ion is going to be much more reactive at C2 towards nucleophiles. And so this will undergo nucleophilic addition very, very readily, and much more readily than pyridine itself. Now the problem, of course, is that the N-methyl group is not, it stays there. So you don't end up with pyridine at the end of the reaction. At the end of the reaction, you have an N-methylamine, which may or may not be useful. But you can do the same trick using a pyridine N-oxide. And so if I just start with the pyridine N-oxide, here also the pyridine has a partial positive charge. And so nucleophiles will add rather readily to the pyridine N-oxide, like so, and this reaction will be much faster than with pyridine itself, because the pyridine is charged. And so getting to the corresponding, there's a hydrogen here that I'll show just so we don't lose track of it. So getting to this kind of nucleophilic product is quite easy. Now here, you actually can regenerate the pyridine just by treating this with acetic anhydride, as I showed. It ends up being kind of a dehydration. If you think of this getting protonated, then this will so in workup, this will protonate. Let's just show that. So this is the initial product you get out of the reaction, but when you treat this compound with aqueous acid as you do, then you end up with an OH. And so if I just think of this is supposed to be hydrogen. So if I just think of removing water from this species, I end up back with my pyridine. And so it's quite easy to use the pyridine N-oxide to end up with two substituted pyridines. That's probably the more practical way of doing all this. So the N-oxides are kind of chameleons. They are very good acceptors at C2, and they're good donors at C4. Okay? So you can do you can use these either in nucleophilic aromatic substitution or electrophilic aromatic substitution chemistry. So this is what I said. Now, pyridine chemistry is actually quite rich compared to, say, benzene, but all of these reactions are, with the exception of the Chichibabin reaction where you lose hydride, every other reaction is easily understood based on first principles, okay? Okay, so that's kind of a little summary of what we talked about last couple of times. Now let's get to pyridoxal and pyridoxal phosphate and all that stuff. So these are all forms of vitamin B6. And vitamin B6 is an enzyme cofactor. Remember what a cofactor is. A cofactor is a small molecule, small organic molecule, that reacts with an enzyme to affect some kind of chemical change. So think of a cofactor as being a reagent, but a reagent that works in tandem with an enzyme. And so these are all cofactors that react with various types of enzymes to do some very amazing chemistry, actually. So the pyridinium ion is what drives this process. Seems kind of silly, pyridinium ion. How can that possibly drive anything? It's just a protonated form of pyridine. But you'll see how that works. And it catalyzes. It turns out that pyridoxal catalyzes a number of very strange reactions. I mean, here's one that's kind of weird, right? It's the decarboxylation of an alpha amino acid. So we've talked about decarboxylation reactions in the context of beta-keto acids, right? We said that if you have a beta-keto ester, you hydrolyze it to a beta-keto acid, you treat it with base or with acid, spits out CO2 very easily. Because why? Well, because we have that special transition mechanism for doing the decarboxylation. So if you have any kind of carbonyl, it doesn't have to be ketone, by the way, it could be another ester or an acid. But if you have a hydroxy group like this, then you can get this kind of chemistry in base, which gives you CO2 as one product. That's volatile and it goes away. And you end up with the enolate of the whatever it was, ketone or whatever, on the other half. And so this reaction depends, the decarboxylation depends on having this carbonyl group. And the way your book describes this is actually quite nice. It says that, well, really what you need is you need a place for this electron pair to go. Okay, so this bonding electron pair ends up as one of the electron pairs on the enolate. So you need kind of an electron pair sink to get this process to go. Now, the reason for that is that if you don't have that, imagine what happens if there's no carbonyl here. Okay, so just think for a minute, what if I didn't have a carbonyl? How would this process go? So let's just go ahead and show what would have had to happen if we didn't have an oxygen for that electron pair to migrate through, so to speak. So if we just had this kind of a structure, okay, where this is negative charges in oxygen. If we had just this kind of a structure, then what would happen? Well, if I push arrows the same way, I can still form CO2, but now this electron pair has to sit on that carbon atom. And so instead of having a resonance stabilized enolate with a negative charge and an electronegative oxygen atom, what I would have here, there's the CH2 there, what I would have is I would have a carbanion. And so this carbanion, of course, is going to be very high in energy because the negative charge is on a not so electronegative carbon atom. And so that's why this process doesn't take place except under extremely forcing conditions, whereas this reaction takes place at roughly room temperature. Okay, so the key is having some place for this bonding electron pair to migrate to. Now, the one place that you can migrate that to is a pyridinium ion if you're using pyridoxal phosphate as your cofactor. So we'll see that. So this process, we'll go through the mechanism, depends on forming an imine from this amine to that aldehyde. Okay? So that's one. So decarboxylation is one reaction that pyridoxal phosphate can mediate. It's not the only one. The other ones are something that's called transamination. So let's just show it here. So what's a transamination? It's just what it sounds like. You start out with an alpha amino acid and an alpha keto acid. Okay, so two related species, so to speak. And you throw in an enzyme, You throw in pyridoxal phosphate as a cofactor, and what happens is you end up getting the ketone where you had the amine, and the amine where you had the ketone. So you convert one amino acid to a different amino acid. Okay? So this is what's known as a transamination. So you can think of it as just kind of grabbing that amino group and going and gluing it onto where the keto was. Okay? Now, it doesn't work that way, of course, but this is another reaction that is mediated by pyridoxal phosphate. And finally, the cleavage of formaldehyde from serine. This is more or less, the mechanism is more or less the same as the decarboxylation. It's not quite the same, but it's almost the same. So look at what you do here. You start out with serine, and then you end up with glycine. So you end up cleaving the CC bond. Now, cleaving that CC bond doesn't look all that hard, but under physiological conditions, it is fairly difficult because the carboxylate is deprotonated. So here's what I mean by that. Okay, so let's take a look at and see what this process actually looks like in a different context. Okay, so let's just say that I have cyclohexanone, and I have this cyclohexanone here, 2-hydroxymethyl cyclohexanone. What do you think happens if I treat that with potassium p-butoxide or some strong base and I heat it up? Think. So I take a strong base, I throw this in. What happens? What's the first thing that happens? Deprotonation. Okay, so with base, the first thing that's going to happen here is I'm going to end up with the alkoxide. Okay, now what I want you to do is I want you to push arrows the way I pushed arrows with the decarboxylation. Do it in your head. Okay, just push arrows the same way. So if I were decarboxylating this, what would I, and this is a reaction you've seen, right? If I were decarboxylating it, it would look like this. And pushing arrows would give me this enolate with loss of CO2. I can do it the same way here, form the same enolate, but with loss now of not CO2, but of, you guessed it, formaldehyde. Okay? So loss of formaldehyde can take place. That's a reaction you've seen in the opposite direction. That's a retroaldol reaction. Okay? So the aldol reaction would be the enolated cyclohexanone and formaldehyde giving the hydroxyketone. This is a reverse of an aldol. That's just a retroaldol reaction. So it looks very, very much like the decarboxylation. Okay? So, so the serine to glycine transformation is in fact a retroaldol, nothing else, a retroaldol reaction. But it's a difficult retroaldol without the enzyme because why? Well, because think of the enolate I have to make. I have to make the enolate of a carboxylate. That's a dianion, no good. And so that's why you need to have the cofactor, and that's why you need to have that pyridinium ion to suck up that electron pair so that you don't ever get a dianion that's high in energy. Okay? So, so let's see how pyridoxal manages all of this. And the way it manages it is it's so simple, but it's really clever. So let's take a look. Okay, so you have the enzyme. And the enzyme has a lysine on it, which is it's an amino acid with a straight chain terminating in an NH2. And we're going to let this react with pyridoxal phosphate. And you know, I'm going to use instead of showing all of the substituents, I'm just going to put lines there, and you'll know that I have a hydroxy group here and a hydroxy methyl phosphate and methyl here. And but the business end is going to be the aldehyde. The other business end is going to be the pyridinium end. Okay. So what happens when I take an amine and I allow it to react with an aldehyde? Ketones too, but aldehydes really fast. What happens when I take an amine and I allow it to react with an aldehyde? You don't even have to add a catalyst. I mean, this reaction takes place really, really fast. We saw this reaction when we talked about reductive amination reactions, the formation of an imine. Okay, so this acts as a nucleophile, that's an electrophile. It adds, forms a tetrahedral intermediate, proton transfers take place, you spit out water and you get an imine. Now this is an equilibrium. So I end up with the enzyme, and then I end up with that as my imine. Okay, so this functionality here is an imine. Okay, and the hydrogen is still there. We haven't lost it. It's right there. Okay, so you end up forming an imine. Okay, fine. Now, what will happen next is the enzyme, having transferred this amino group here, is going to react. Oops, NH2 plus. Okay, so here's the amino acid. Everybody see that? And so you'll end up with an imine exchange. So this nitrogen ends up replacing the enzyme. Now, we'll talk about how this happens in a minute. So this reaction here is going to be known as imine exchange. And so what we will have for the amino acid is we'll have this species, and this nitrogen now is going to engage the pyridoxal phosphate. Okay, so now let's talk about, and we'll end up with the enzyme. So the enzyme is regenerated in this step. So the enzyme with the amino group is regenerated. Now, so this is the imine exchange. Now, how did that happen? What had to happen in order to get that imine to flip over or to exchange? What was the first thing that had to happen? It's something that happens with, very fast and with low activation barrier. What is that? Common feature of a lot of these mechanisms. Okay, so think of it this way. Here's how you think about it. Can this nitrogen form a bond to anything? No. Why is that? Well, because it has a complete octet. So this, and yet, it did form a bond to something. So how the heck did that happen? Well, it had to lose a proton, didn't it? Because if it doesn't lose a proton, it can't do anything. So the first thing that happens is proton exchange. And so you end up activating this amine with a proton, and you end up activating this as a nucleophile by loss of a proton. So you end up, so the first thing that happens is, we'll go down here and I'll show this. Okay, here's the enzyme. Here's the imine that we started out with from the pyridoxal phosphate. This picks up a proton, which puts a positive charge there, and in the process, it activates this carbon towards nucleophilic attack. Right? So once this is protonated, now this is a much better electrophile than it was before it was protonated. So this imine picks up a proton right there, gives you this. The amino acid, that's this one, loses a proton. And so let's show that here. To give you this, now this is a much better nucleophile than it was. It is a nucleophile. This is not a nucleophile, so it's not a question of better. That can add to give you a tetrahedral intermediate. Now that tetrahedral intermediate is one we haven't really looked at very carefully, because it's one where you have two amino groups bonded to the same sp3 hybridized carbon atom. And so and I'm going to abbreviate this just because in the interest of time. So if I have the enzyme, then I will have the pyridoxal. Let's show that like so. And then the bond that I made to the amino acid is here. And I'm going to abbreviate the rest of the amino acids just an R group. Okay, so now I've got carbon atoms bonded to two nitrogens. To go from here, where this is the amino acid, to there, what needs to happen? Well, proton transfer, loss of a proton, addition of a proton, and then loss of the enzyme. So this whole business, once it's protonated, acts as the leaving group, and you end up with this imine. So it's, does this look any different from the chemistries that we've talked about, the mechanisms we've talked about up to now? No, it doesn't. It's exactly the same kind of mechanism that we see. You end up with either a carbonyl or an imine, gets protonated, get nucleophilic addition, tetrahedral intermediate, proton transfers, collapse, and so on. It's always the same, okay? So, now, once we're at this stage, and I should put these substituents here so that we know they're there. Once we're at this stage, notice that I'm primed to get decarboxylation. Why? Well, because now I have a place for that electron pair to migrate to. The place it migrates to doesn't give me a carbanion, which would be very high in energy, because the pyridine is protonated, I end up with a neutral molecule. In fact, this whole thing is neutral, right? It has one negative, one positive charge. So when I lose CO2, like so, then what will happen is this. I'm going to end up with CO2. There's the CO2. That escapes as a gas. Double bond here, single bond here, double bond there, okay? I end up with a neutral molecule. And so that's going to be much lower in energy than forming any kind of carbanion. So that's why the loss of CO2 takes place with such low activation carrier in this context. Because you're not generating an energetic intermediate, you're generating a rather stable intermediate. Now, once we're at this stage, we still don't have an amine, do we? So how do we go from this imine to the amino group that we discussed? How does that happen? So remember that this whole piece has to regenerate pyridoxal phosphate, and it has to generate, so it has to generate this thing, but it also has to generate an amine here. And so that's kind of weird, isn't it? Because look, this carbon atom is oxidized, right? This is an aldehyde equivalent. And if I want this to be an amine, then that would be a reductive amination product, wouldn't it? But this pyridine ring is oxidized. And what I want is a reduced form. I want pyridine. And so what's going to happen here is an intramolecular redox kind of reaction, where the oxidation where you end up reducing one group at the expense of the other. So let's show that. Okay, so let's go over what I just talked about first. So you have an enzyme, you have pyridoxal phosphate, you form an imine. You allow the imine to react with an amino acid. This has to lose a proton first. You get that transamination, that transamination reaction where this imine gives rise to a different imine. That's from that tetrahedral intermediate. And then here you're primed for loss of CO2 because the electron pair can migrate into the pyridinium ring. And so loss of CO2, you can imagine how you push electrons, because I showed you how to do that. and here it is again, that you end up pushing electrons from this carboxylate to form a different imine here. And the resonance, I didn't show you this resonance structure, I showed you this neutral one. But the importance is, this is the important one, because this one has no charges. However, we're still not there. Remember that the reaction we're talking about is a transamination, and so I need to end up with just a amine, not an imine. And so somehow this imine has to turn into an amino, and then I have to regenerate the cofactor. This just goes over what I said. Okay, so the reaction takes place not in free in solution, but in the active site of an enzyme. And so the proton that you need a proton for this process, is provided from the enzyme. So this red proton protonates this carbon atom. Now you can say that, gee, I would have expected protonation to take place on nitrogen, not on carbon. How does that happen? I mean, if I had an imine, what? If I had just a plain vanilla imine, then what's the most basic site for protonation to take place? So if I just have, this imine here, let's just say cyclohexyl, is what will happen. And I treat this with a proton. Where's the protonate? The protonate right here, because the nitrogen atom is the more basic of the two, and so with a proton, what happens here is you end up with protonation like so. And this is resonance stabilized. I can show resonance form that places the positive charge there. So that's the expected site of protonation, right? But look here. Protonation didn't take place on the nitrogen lone pair. It took place on carbon. How come? Pardon? Yeah, so it's essentially the same thing that I just showed you, except instead of this electron pair, it's this one doing it. Look at this. So you have this electron pair, and it moves around, so to speak, to pick up a proton, generating an iminium ion here rather than the iminium ion there. And so having the pyridinium, or the pyridine in this case, ring, ensures that you get a low energy pathway for protonation to take place not on the imine nitrogen atom, but on the imine carbon atom. There it is. Now this generates the imine of pyridoxal phosphate, and I made a mistake there. This line should be there, but it doesn't change anything. And now all you need to do is just hydrolyze that. So this picks up a proton, gives you the iminium ion, water attacks, that gives you the amine and the aldehyde, and you're there. And so this is how enzyme catalysis works, right? You end up, in fact, this is how catalysis works. What you end up doing is you provide a pathway for the reaction to take place that's low energy. So think of it as navigating a mountain range. On one side of the mountain range, you want to get to the other side. So what the enzyme does is it allows you to find the mountain pass that has the lowest elevation, lowest activation energy to get from one side of the mountain range to the other. And so you're not really changing the starting material, you're not changing the product, same starting material, same product. The enzyme is regenerated. Notice that the cofactor is also regenerated, but you have a low energy pathway for getting there. And for the reasons that I indicated, that even though you're protonating on a carbon atom here, In fact, you're getting an aminium ion as your product anyway. So this is really a very clever enzyme. Now, the key to all of this, to all of these reactions, the key is having a protonated pyridinium ion. Obviously, if that pyridine had not been protonated, none of this works, right? I mean, everything relies on having that thing protonated. And so now there's kind of a funny thing that goes on, because at pH 7.4, which is physiological pH, which is the pH at which all this stuff happens, the physiological pH, that pyridine, if it was just a pyridine, it wouldn't be protonated very much, because the pKa of the pyridinium ion is about 5. So pyridine would be present as plain old pyridine. And so, I mean, you have about 1% maybe of the pyridinium, but that would not result in good catalysis. And so the design of this cofactor, if you will, using a term that I guess will offend anybody, all the biologists, but you know what I'm talking about. I'm not talking about intelligent design, I'm talking about the evolutionary design, being politically correct. So the evolutionary design of this thing is really tuned very carefully, because having the phenol, having this phenoxy present, greatly increases the basicity of the amine. And so that means that having a negative charge here, 1, 2, 3 bonds away from a positive charge, stabilizes still this pyridinium ion and renders it stable in the protonated form. So it turns out that this group here is critical. Absent this, none of this stuff works. And so that phenol is a critical feature of the cofactor. So because the resonance structure is shown, the pyridinium ion, the pyridinium ion is more basic than you would expect. In other words, the phenol is more acidic and is stabilized, and so you end up with essentially everything present in the protonated form at equilibrium. And so, it's a nicely tuned system. And the mechanisms for the other two reactions that I showed, which were transamination and the serine to glycine transformation, those I believe are given to you as problems in the text. And I urge you to try to go through those. Those are very big problems. You can do this kind of chemistry, you really understand not only this chapter, but also the ketone chapters much better than much better. Okay, so one of the other things that this chapter covers, it covers a little bit of DNA and RNA chemistry, which I won't go through in quite as much detail as the book. This is stuff that you will see in a biochem course, but we'll talk just a little bit about nucleosides and nucleotides and nucleic acids and whatnot. So the building blocks of DNA and RNA are very similar. The difference is that in DNA, you have one less hydroxy group on the sugars, and you have a small change in one of the bases. So let's first go to the sugars. The sugars we can show in two different forms. If you show it this way, it means that these bonds here, maybe I should make them shaded. If I make these bonds shaded, then these are in front of the screen, and the oxygen is behind the screen. And then these hydroxy groups are pointing down. Hydrogens are up. I've not shown those. And I have hydroxy groups. So this would be ribose, D-ribose. And the numbering is, you start from the acetal carbon. This is the aldehyde carbon, right? And so 1', 2', and so on. So this is D-ribose. Ribose is the sugar that's in RNA. In DNA, you have deoxyribonucleic acid, so it's deoxyribose, the 2' deoxy. And so this is the sugar that forms the backbone in DNA. This one is in RNA. Now, attached to, so in place of this oxygen, there's a nitrogen atom provided by one of these bases. So it's either this nitrogen or that one, or this one, or that one, or that one. And these are the bases. So GA are in both DNA and RNA. TC is only in DNA, and this only appears in RNA. And so the two molecules, the two macromolecules, DNA and RNA, are very, very similar, but they do have some differences as shown. So imagine now for DNA that you have this sugar, but instead of having an oxygen atom, you have this nitrogen. So you have a bond from this nitrogen to that carbon. Okay? These nucleic acids, these bases, pardon me, have these abbreviations, so adenine, guanine, and so on. Okay, so you've probably seen this all before in a bio course, and you kind of know what's coming next. What's coming next is the discussion of how the sugar and the amine base fit together, and then what else is present. And so if I have what do we say? We said a nucleoside. Then a nucleoside is one of these sugars and one of these bases. And so if I take adenosine, I have ribose and adenine. Okay, so here this is the aldehyde carbon atom. The aldehyde carbon atom is bonded to an oxygen and a nitrogen. So if I hydrolyze this in aqueous acid, I'll end up with an aldehyde right there, right? And I'll end up with adenine as the base. So this is a nucleoside. So any nucleoside is a combination of a sugar and one of the bases. And then if I have a nucleotide, it turns out that the C'5 oxygen is phosphorylated. And so this is the structure of the currency, of the energy currency in your cells, ATP. Okay, so adenosine triphosphate is this stuff here, where I have 3 phosphate groups. And phosphoric anhydride bonds, each one of these is about 7 kcals per mole. And so this is how your cells traffic in energy. And so this would be a ribonucleotide because it uses ribose, not deoxyribose, as the sugar. And so this is, ATP. Okay. Now, ATP is not found in DNA or in RNA. The sugars are monophosphorylated in the nucleic acids. Now, there's a strange thing that people notice. It's actually not strange, but it's key to understanding what's going on. And that is that in DNA, the ratio of adenine and thymine is equal to guanine and cytosine, and they're both equal to 1. So in other words, you have just as much of A as you do T, and just as much G as you do C. Doesn't mean that you have the same amount of A and G or T and C. It just means that these 2 quantities are identical and these 2 quantities are identical. Proportions are identical, I should say. So it looks as if there's something special going on between G and C and A and T. And the one thing that's special is that they form complementary hydrogen bonds. So if I look at A and T, so there's the adenine, imagine a sugar here, imagine a sugar there, then I have these hydrogen bonds that can form that hold the 2 strands of in this case, the DNA, together. Okay, so those hydrogen bonds are worth some energy. And if you have a lot of them, of course, more, because it's a big molecule. And G and C form 3 complementary hydrogen bonds. So that's why for every C there's 1 G, for every T there's 1 A, and that's why this ratio is always 1. Because in order for the double strand to form, you need to have this hydrogen bonding situation. So now the question, of course, that everybody has is it only the hydrogen bonds that are holding the strands of DNA together? The answer is no, it's not. there's something else going on too. And the something else is something we've seen. You'll notice that the bases here are kind of flat, okay? And if you imagine the overlap of the electron pairs, say on this imide nitrogen with the 2 carbonyls, these are all flat rings. What do we know about pi stacking? Remember we talked about pi stacking way back when we talked about benzene, we talked about aromaticity, 272. Well, here it comes back. It turns out that another reason that keeps those strands of DNA together is because each one of those bases has electron density that seeks out electron density in the adjacent base. And that turns out to be very important for stabilizing the structure of DNA as well. So you have two things going on. You have the pi stacking, and you have this hydrogen bonding. Disrupt either one of those two and you screw up the DNA. Now, how do we screw up, we talked about actually, how do you screw up the pi stacking? You may not remember, I said, when we talked about oxidizing phenols to quinones, I showed you the structure of donomycin. Remember, that was an anti-cancer drug that had an anthraquinone and it had some other stuff. I said that this was a DNA toxin. And so the anthraquinone fits in between the base pairs, the bases, and disrupts the structure of DNA, and other things happen. So that's one way you can disrupt DNA. Find another flat molecule that fits in between two of the bases, and all of a sudden you destabilize the structure. The other way is to wipe out one or more of the hydrogen bonds. And you can do this quite easily by alkylating the DNA. And so anything that will disrupt the hydrogen bonding is going to destabilize the structure of the nucleic acid, and it's going to end up in what's known as a DNA lesion. And so it's the same thing for RNA too, but let's talk about the DNA. So a DNA lesion, which is unrepaired, then prevents the faithful replication of DNA. So in other words, as you all know, DNA and RNA are self-replicating molecules, and so when you unwind it, you end up making copies of each of the two sides, and then you end up going from one DNA molecule to two. That process depends on having intact DNA monomer on both sides, or single-stranded DNA on both sides. Once there's a mistake somewhere in there, then that process doesn't take place. Now, it turns out that these kinds of mistakes take place all the time, and these kinds of mutations take place all the time in the course of our day-to-day life. But that most of us have functioning repair enzymes that address these problems. If your repair enzymes aren't working very well, or if they're overwhelmed, then there's some very big problems. One way to overwhelm them is to add an alkylating agent in fairly large quantity to a cell. Now, these are all compounds that can transfer a methyl plus, so to speak. So we've seen all of these. And imagine these as being the electrophiles in a what? In a SN2 reaction. Boy, back to Chem 272. We thought we'd never hear that stuff again, but no, it is. Okay, so let's take a look at dimethyl sulfate. So dimethyl sulfate is the methyl ester, if you will, of sulfuric acid. Think of this piece here as O minus SOCH3, okay? This is a very weak base. It's a very strong acid if it's protonated. That means that it is a very good leaving group, correct. So any kind of nucleophile, an electron pair, will do this chemistry very, very easily. And so that's why this is a good methylating agent for DNA. Same thing for methyl mesylate. This is mesylate. And methylfluorosulfonate is, this is the stuff I told you about called magic methyl that the poor guy got himself killed when he spilled it on himself. And so these are very powerful alkylating agents. We'll talk about this when we meet on